This is part 12 of our series of discrete probability lectures. This is talking about the discrete uniform distribution. In a discrete uniform distribution, there are a finite number of values of the random variable, and let's say there are n of those, and the PDF is a constant function. So the probability is the same, in other words uniform, for every possible value of x. So all the probabilities are the same. So your probability density is kind of spread out evenly among all the values. And if there are n of those, that makes the probability 1 over n. The graph will have bars all the same height. So probably the easiest example I can think of that would be a good example of this would be our good old rolling a dice experiment. We let x be the number of dots on the top face. The values of x could be 1, 2, 3, 4, 5, or 6. They're all equal probability, so they all have probability 1/6. The PDF is just p of x equals 1/6 for every x. And when you graph that, of course, there'll be bar graph with all the bars the same height. In this case, the mean is just the mean of the actual x values. You don't have to really think about the probability too much because it's all spread out evenly. So remember, the mean is the expected value of x, mu equals expected value of x, and it's a sum over all the x values of x times p of x. Well, p of x is 1 over n for every 1, and we have an x sub k for every k going 1 to n. Factor out the 1 over n, and you see the formula there that is exactly what we got for a population mean when we had a population of data. So really, the mean is the same idea as we had in a data set. If all the values have equal probability of happening, that's what we have in a discrete uniform, and we can just do the mean. Of course, we can use our calculators to do this. If we can just type in all the x values in a list and use our statistics from our list to figure out the mean, and this also works for the standard deviation as well. Since they all have the same probability, the population variance and population standard deviation of the x values will be the variance and standard deviation of the distribution as well. So notice that sigma square, which is the variance, is the expected value of x minus mu square. So it's x minus mu square times p of x. But all the p of x's are just 1 over n. We can factor that out or write it as a fraction with that 1 n in the denominator. And what are we doing? We're adding up all from k equals 1 to n, all the x minus mu squares, dividing all that by n, and that's exactly what we computed for the population variance before. So when we have a uniform distribution, we're just basically taking the mean of the x's to find the mean of the distribution, and we're finding the standard deviation of the x's to find the standard deviation of the distribution. It's when your probabilities are a little bit different for each x that has to come into the weight of things, and that's where this times p of x comes into play. So that weights each one of them if those p of x's are variable. So there's a really brief introduction to a discrete uniform probability distribution.